Okay, so I'm totally losing my voice, but I'm pretty sure that we all somewhat saw this slide or we're about to see this slide today. We talked about water, we talked about him being a polar solvent and the universal solvent. Now we're going to talk about solubility rules and how do we know what to expect from a reaction before it actually happens. And so the first thing you need to know is this word soluble. They used it a lot in your notes. I don't know if they explained it clearly, but soluble just means that it does dissolve in the solvent. And so we put that symbol AQ on the end. We already know that that means aqueous. We used to say aqueous just means it dissolves in water, but now we're talking about other solvents that could be things like gasoline or turpentine or who knows what. So anything that you could dissolve something in is considered a solvent. And so soluble means it's aqueous. So the two things are going to mix. You're not going to see the different parts and it's going to be evenly blended. If it doesn't dissolve, it is insoluble. And so it's got this S designation. And in some classes, we talked about that that S does not mean soluble, that S means solid. So even if you have these two words somewhere in your notes, you definitely are going to want to add these two symbols next to those words so you remember which is which. Here's the word we always forget. The word precipitate. If you remember the day that I took the flask and the test tube of clear liquids and I dumped it upside down real quick and it turned bright yellow, like out of nowhere. And I walked around and I showed you the yellow powder that got produced, that was a precipitate. So we would say that whatever that compound that got made was insoluble in the new liquid. So this is something that we used to teach when we had the STAR 2 years ago. We teach it all the time, but this new format was on part of your STAR chart. So this is on your yellow formula chart on the back. So it's not a bad idea to reference what that looks like. But let me show you how this works. So you find a compound and they want to know, okay, if I put this compound into water, I want to know, is it going to dissolve? So these are solubility rules in water. We're not talking about gasoline or turpentine, we're talking about water. So you've got some copper nitrate. So you come over to the list over here, and you find nitrate. So I find him, he's right up here. And when I look at nitrate, he's on the soluble list. And so then I look over here and find out that he has no exceptions. And so all nitrates are soluble. That means I can wash them all down the drain because they mix really great with water. So the symbol that copper nitrate would get is AQ. So let's try another one. We look at magnesium carbonate. You'll notice that everybody on these lists over here are negative. And so we're not looking at the first guy. We're looking at the second guy. We're looking up carbonate. So we find carbonate on our list. He's on the insoluble list, but then we have to check out these exceptions. Check these out. If the carbonate's attached to NH4, it's not insoluble. That means he would be soluble. If he's an alkali metal, most of us have forgotten that alkali metal means group 1. So since he's not attached to anyone in group 1 either, then we're going to go ahead and say that this carbonate is insoluble. If it was a group 1, again, it should be on the soluble list. So this magnesium carbonate is insoluble since magnesium's not an exception. So we're going to put an S designation on that, meaning he will form a solid. When two liquids mix, he will form a solid and sink to the bottom. He will not mix with water. So he would not be a good one to wash down the drain. Let's do another one. Ammonium chloride. We find chloride on the list. Here he is over here. We go to our exception list and say, is he attached to silver, lead, or mercury? The answer is no. Ammonium's different. So we stick with the rule that says he's soluble. So he's an AQ. We look up sodium hydroxide. Hydroxide is way down here on the list. And so when we're looking up sodium, we have to ask ourselves, is it ammonium? No. Is it attached to an alkali metal? And the answer is absolutely. Sodium is an alkali metal. So instead of being on the insoluble list, he's going to be on the soluble list. And so he also gets an AQ designation. Next, we've got magnesium hydroxide, another hydroxide. So we look, but we find out, look at here, we've got calcium, strontium, and barium who are all in group 2, but magnesium didn't make the list. So magnesium is not an exception. So this hydroxide is insoluble. So I'm going to put a solid symbol on him. Last one, we've got some lead chromate, and chromate is over here. Whoosh. Chromate, we check it out, not attached to ammonium, not attached to a group 1, so again, he's insoluble. So that's how you use the chart on the back. It's really kind of nice. As chemistry teachers, we just kind of know some of the rules. I used to know all of them by heart in high school. I don't know them all anymore. But hopefully with some practice, we'll start to learn some of them, and we won't have to look at the chart quite as much. So let me show you the practical application of this. So if we had some reactions like we have here, we are going to predict products just like we did in the chemical reactions unit. Good news, they're all double replacement. And so we should very easily be able to see that the sodium and barium are going to switch places. The barium comes over with his +2 charge, hooks up with the sulfate with his -2 charge. The 2's cancel. There's your barium sulfate. And the sodium is now going to hook up with the chlorine. The +1 and -1 cancel out. There you go. We got to put a big 2 in front of that to balance. But we're not done. So now we want to also predict whether these products are soluble or insoluble. Little trick. Anytime you have a double replacement, both of the reactants are aqueous. So I already know without looking them up that everybody on the left side of the arrow is an aqueous designation. Now what we have to find out is tell me about the right side. So we have to look up our sulfates, and we have to figure out if our sulfates are soluble or insoluble. So go back to your chart, find sulfate, see what list he's on. Sulfate is on the soluble list, but it's attached to barium, which means he's an exception. So because he's an exception, he is actually a solid. So there's my precipitate that formed. And sodium chloride, theoretically, you don't need to look that up. You know that salt dissolves in water. So he would get the AQ. We're not going to do this example. I think you probably are with me at this point. Let's do one last one because it's kind of odd. When we flip our 2 cations, we get iron. Keep in mind that that 3 used to be up here. So he's going to bring his +3 charge. He's now going to hook up to nitrate. Have to crisscross that 3. The -1's imaginary. So all that goes away. And now we've got potassium chloride. +1, -1. Everybody cancels. And we balance. Oh, wait. I balanced for you over there. So I had a 3 in front of potassium chloride, and you're done. So now, when we go to predict the products here, we find out that we look at nitrate. What list is he on? He's on the aqueous list. Then we go look up the chlorides, and we find out that potassium chloride is also aqueous. Now think about this. If I took 2 clear liquids and I mix them together, and I get 2 clear liquids, nothing's going to happen inside that beaker. So technically, if everybody's aqueous on the right side, there was no reaction. And in chemistry, we like to put arrow NR, which means we're not going to see anything. There's no cool precipitate, there's no bubbles, there's no heat, there's no nothing. We literally dumped a bunch of stuff into the same container, and all the ions are floating around together, but nothing interesting happened. So I just wanted to show you an example of that. That could happen. Usually we're not going to give you those kind. So none of my classes got to this point, but this is pretty much common sense. So check this out. You're going to need to pay attention to this part for today's assignment. If we're talking about solubility, solubility, definitely need this definition. It's the amount of a substance required to form a saturated solution at a specific temperature. So basically, how much salt can I dissolve in room temperature water? How much sugar can I dissolve in room temperature water? If I heat that water to 90 degrees, how much sugar can I dissolve now? How much salt can I dissolve now? That's the solubility of a substance. The solubility is definitely dependent on the temperature. Usually when the water's hot, it dissolves more stuff. When the water's cold, it's not very cooperative. So here's my example. When water is slightly below room temperature at 20 degrees Celsius, it can dissolve 204 grams of sugar. That's a lot of sugar. So that is the solubility of sugar at 20 degrees. If we raised that temperature up to 100 degrees, which is boiling, this number is going to increase and be way greater than 204. And so that's how Chicken Express makes their sweet tea. They make their water super hot. They dissolve a ton of sugar. They cool it back down, and you've got super sweet tea. So if we wanted to talk about how can we make the sugar dissolve faster, there are three things that we can do, and they're common sense, but listen to this explanation. Of course, when you're making Kool-Aid or lemonade, you stir it, you agitate it. Why would you do that? You're increasing the number of collisions, and when you do that, you've got more water hooking up with more sugar, and the more they bump into each other, the more that water can surround that sugar and hide it between the molecules, like we talked about yesterday. So that's the first way that you can make things dissolve faster, by stirring way, is to heat it up. You already know when things get hot, they increase the kinetic energy. Again, more frequent collisions, they're going to bump into each other more, and the more they bump into each other, the more they're going to hide that solute in between the solvent. So we're trying to increase the number of collisions. So after we stir it, after we heat it, if it still won't go, crush it or grind it. So if we have a big clump like a sugar cube sitting in the bottom of our container, we can take our wooden spoon and just annihilate it and crush it up into thousands of little pieces. And when we do that, we're mixing up the solute and the solvent, and we're just getting the water to touch more pieces of that sugar. So the more water that touches more sugar, we're increasing the surface area. Okay, we're decreasing the particle size, increasing the surface area, and again, it's all about those collisions. Okay, so we can stir, we can heat, we can crush. Remember those three. That's how we make it dissolve faster. Now, misconception. Doing all three of these things is not going to make it dissolve more. It's just going to make it dissolve faster. Faster. So, now, how can we make it dissolve more? So we talked about how to speed it up by stir heating and crushing. Now, how do I get more sugar into that sweet tea so everybody comes to my business to buy my tea? So we already know about solubility. Solubility is the amount. The first factor that affects how much will dissolve is the polarity. Remember we talked about water being polar. So here he is with his positive ears and his negative head. What's going to happen is that we say things that are like will dissolve things that are like. You need to write this down, okay? Like dissolves like means polar will dissolve polar, or things that look like they're polar. Today we talked about salt, or yesterday we talked about salt dissolving in water. Water is polar, salt is ionic. So polar will also dissolve things that are ionic, because polar means positive, negative. Ionic means positive, negative. So basically, if something is polar and it dissolves polars and ionics, who will it not dissolve? It will not dissolve things that are non-polar. So the nature, we call it the nature of the solute and solvent. Things that are alike will dissolve in each other. So if a nonpolar gets put in there, you have to add another nonpolar to the container for these two to actually mix. Nonpolars and nonpolars love each other, but nonpolars and polars hate each other. So look, this is a pretty good rule of thumb. I just said that the polars will dissolve the polars and ionics. So water who's polar dissolves salt who's ionic. Water who's polar dissolves sugar who's polar. How do you know sugar's polar? Because when you look at his little chemical structure with all of those little doodads that were sticking off, it's not symmetrical. It's kind of crazy shaped. Anything that's crazy shaped is considered polar, and it will dissolve in things that are polar. Nonpolar means it looks alike all the way across. And so if you looked at a chemical like carbon dioxide, oxygen, double bonded to carbon, double bonded to oxygen. If I split it in half, it's symmetrical. Split it in half again, it's symmetrical. So nonpolars will dissolve other nonpolars. Oil will not dissolve in water, but it will dissolve in gasoline, which means that they are both nonpolar. If we wanted to fill out this chart, let's think about it. We already know that water is polar. I'm telling you over here that turpentine is nonpolar because you're not really familiar with that. You might have some in your garage. It helps to get paint off of paintbrushes. It's used as paint thinner. It's used as a really good garage cheap solvent you can buy at Home Depot. Then you look at a chemical like bromine 2, Br2. It's a Hofbrinkel. That means bromine is hooked up to bromine. Split it down this side, symmetrical. Split it down the middle, symmetrical. So we would say that bromine is non-polar. So I'm going to label him with an NP. P, NP. NH3, I would draw it if it was me. If you remember, the single atom goes in the middle. So here's N. The H's surround him. Bond 1, bond 2, bond 3. If you added up all of the available electrons, nitrogen's bringing 5. The hydrogens are each bringing 1 3 times. That's a total of 8 electrons. We've used 2, 4, 6. That means we still have 2 remaining. So there's a lone pair right here. Anytime there's a lone pair on the center atom, that compound is going to be polar. Lone pairs make you polar. So let's decide, are they going to be aqueous or solids? Polar will not dissolve nonpolar. So that is a no. So that means they are not soluble. Polar will dissolve polar like dissolves like. So we are going to say that that guy is soluble. Then we've got turpentine, who's nonpolar, with bromine, who's nonpolar. They are alike. So he is going to be soluble. And then our last example, nonpolar with polar, they are opposites, so they are not soluble. Don't worry if you can't figure one out on the assignment today. Do the best you can, and we will make do next week. But do the ones you know. Ask the sub for permission to use your phone to look it up, but it should be a less than 3-minute ordeal. You should not have to be on your phone for 20 minutes to find out which compounds are polar or nonpolar. Draw them, look for lone pairs. Anything that sounds like a garage chemical, go with nonpolar. So the last few words for today is the word miscible. Miscible just means two liquids will combine and totally mix. Like, I don't know, fruit punch, liquid fruit punch. If you dumped Gatorade into water, those two things are miscible. They will mix very, very well together. We're talking about liquids now. Dissolves in all proportions. Ethanol is miscible in water. They're both polar. That's how you make a margarita. The word immiscible is another word for meaning not soluble. This is when two liquids will not mix with each other, like oil and water. If we know water's polar, then we should know that the oil is nonpolar. They won't mix. And so the last thing we need to talk about, what affects our solubility, is temperature and pressure. So think about temperature. If you make the temperature hot, then it's going to dissolve more. Hot water will dissolve more sugar than cold water. That makes sense. But if we're talking about gases, think about soda. If we made our soda hot, there are less bubbles. It is less soluble. So graphs for solids always go up ever so slightly because as you make things hot, they dissolve more. But when we're talking about gases, their lines are going to go down slightly because they don't like to be hot. So solids and gases have opposite solubility when it comes to temperature. And then our last characteristic is, now think about this. Pressure only affects the solubility of gases because solids are incompressible. Liquids are incompressible. So the only thing that cares about pressure is a gas. Might be a test question. Might need to know that at some point. When you increase the pressure on your soda, there's a lot more fizz inside of your container. There's a lot more bubbles pushed down into the soda. When you decrease the pressure and open the lid, psh, now you've decreased the solubility, you've made it fizz, now the bubbles are coming out, you're decreasing the solubility. So just remember that this only affects gases. You should know enough to be dangerous today on the assignment. Good luck. Sorry I talked too long. Hopefully you will have a great day. I will see you on Monday. Don't forget the weekend homework, which is to watch the solubility curve video and complete the solubility curve graph homework. Stay vertical. Nothing nasty in your mouth. Love you. See you Monday.